We're going to go through the 7.1 and 7.2 lesson checks that I assigned for homework. They are modified lesson checks, so it's not all the questions. I did sort of shrink it down. So let's start with number 7. How does the momentum change if the mass of an object is doubled? So we're looking at this equation here. So momentum is equal to mass times velocity. We're keeping the velocity the same. We're just looking at what happens if we double this mass. So 2 times the mass that we had before, and we have that same velocity. What happens to momentum? Well, if you do something to one side, you have to do it to the other. So our momentum will double as well. Right? Number 8, how is the direction of momentum related to the direction of velocity? Well, as we talked about in the lecture, both momentum and velocity are vectors, which means they have both a magnitude and direction. Based again on this equation we talked about before, that momentum is equal to mass times velocity. The only way to get the direction of velocity comes from that, the direction of momentum comes from velocity. So momentum and velocity point in the same direction. All right. So we've gone ahead and done 7 and 8. That tells us we are ready for number 11. Number 11, we are going to do some problem solving. Right? What is the momentum of a 0.16 kilogram apple that moves with a speed of 2.7 meters per second? So we have our mass, we have our velocity, and we want momentum. Looking again at the equation we saw before, momentum is equal to mass times velocity. Everything is in base units. We have kilograms and meters per second. Our equation is solved for the variable that we want. We can go ahead and plug and chug into our equation. So 0.16 kilograms times 2.7 meters per second. We do get a momentum of 0.432, and we're going to use the units we used here. We do only get 2 sig figs in this particular case. I will tell you, just a reminder, Mastering Physics does default to 3 sig figs. So this would be a perfectly acceptable Mastering Physics answer. But in terms of regular physics, these are 2 sig figs, so we would go ahead and force that down to 0.43 kilograms times meters per second. All right. That brings us to number 12. We have a school bus with a mass of 18,200 kilograms. The bus moves 12.5 meters per second. How fast must a 0.142 kilogram baseball move in order to have the same momentum as the bus? So let's take a look at that. We have the mass of the bus. Apparently I can't spell the word bus. Is equal to 18,200 kilograms. The speed of the bus is equal to 12.5 meters per second. We have the mass of the ball is equal to 0.142 kilograms. We want to know what is the speed of the ball when the momentum of the bus is equal to the momentum of the ball. Right? That's the overwhelming idea here. We want these 2 momentums to equal, so what does this velocity have to be? Well, let's expand the momentum equations out here. Momentum of the bus is the mass of the bus times the velocity of the bus, and the momentum of the ball is the mass of the ball times the velocity of the ball. Right? We have almost all of these terms. We have the mass of the bus, velocity of the bus, the mass of the ball. We don't have the velocity of the ball, but that's what we're looking for. So when we rearrange this equation for this that variable, we get this. Now it's arranged for the variable that we want. Everything's in base units. We can go ahead and do our plug and chug thing. 18,200 kilograms, 12.5 meters per second, and we're dividing this by 0.142 kilograms. Hopefully you notice that our kilograms over kilograms are going to cancel so that we are left with a unit of meters per second. That's just a sort of another way to help make sure that you are doing this correctly. All right. Hopefully you realize that we have a very large bus going at relatively large speed. So in order for the ball to have the same amount of momentum, it has to be moving really, really fast. And we get that. So we do get 160,112.676 meters per second. Holy cow, that's a big number. We also only get 3 sig figs, so let's go ahead and force that into sig figs using scientific notation. My V ball is going to equal 1.60, all right? I only get 3 sig figs, and the digit after this is less than 5, times 10, and we got to see what that power is. Well, my decimal point was here, and I need it over here. So 1, 2, 3, 4, 5, 6 times 10 to the 6 meters per second. All right? So really, really, really fast. That is like mega meters, so that's a lot. And this brings us to the last question for 7.1. So we are looking at the fact that 2 carts are moving directly toward one another on an air track. Cart 1 has a mass of 35 kilograms, and cart 1 has a mass of 0.35 kilograms at a speed of 1.2 meters per second. All right, so number 14, I'm going to start taking down my notes. I have mass 1 is equal to 0.35 kilograms. V1 is equal to 1.2 meters per second. Cart 2 has a mass of 0.61 kilograms and a speed of 0.85 meters per second. We want to know the total momentum, so P total, of the system, assuming that cart 1 moves in the positive direction. So we know, since cart 1 is moving in the positive direction, that this has to be positive. Because they're moving directly towards one another, that means we have 1 here, we have 2 here. Cart 1 is moving like this, cart 2 is moving like this, that my velocity here has to be negative. Okay. So my P total is going to be since it's a total quantity, P total is going to equal P1 plus P2. All right. So P total is going to equal M1 V1 plus M2 V2, and we can go ahead and keep plugging and chugging. All right, and when we plug that into our calculator, 0.35 times 1.2 plus 0.61 times negative 0.85, we get a total momentum of negative 0.0985 kilograms meters per second. All right, because I had kilograms times meters per second plus kilograms times meters per second. We do need to go ahead and make sure this is the proper number of sig figs. We only get 2 sig figs. All right, so our first non-zero digit is this 9 here. We get this 8, but we got to check after it. That's a 5, so this is going to round up. So my P total is going to equal negative 0.099 kilograms meters per second. Okay, so that takes us through all the questions on 7.1. Let's move on to 7.2. All right. So we are looking at which one or more of the following quantities has the same direction of impulse. Impulse, remember, is a vector quantity. And we are looking at which quantities have the same direction. Momentum itself, while a vector, is not necessarily the direction of the impulse. Impulse is defined as the change in momentum. All right. We could also look at that change in velocity, but the velocity itself is not necessarily the direction of the impulse. Impulse was also defined as force times time. Time, as we know, is a scalar quantity. So like when we talked about the momentum and velocity being in the same direction in 7.1, the force and the impulse are in the same direction here. Kinetic energy is a scalar value, right? So it does not have direction, right? So it cannot have the same direction as impulse. So in this particular case, the same direction of impulse is our change in momentum and our force. So that sort of brings us to number 23. Does impulse determine an object's momentum or a change in object's momentum? Well, it's going to be the change in an object's momentum. Notice that this says explain, so let's talk about it. We talked about the fact that impulse, as by definition, is equal to that force times time interval or a change in momentum. So we're looking at the fact that the momentum of our object is changing as a result of an impulse. This impulse is caused by a force being applied for some particular amount of time. All right? So if we have no change in momentum, if our final momentum is equal to our initial momentum, then change in P is equal to 0. Then impulse has to also equal 0. Right? So impulse is looking at a change in object's momentum. If there's no change, there's no impulse. So that's number 23. Number 24, we're looking at why would a thin steel helmet offer little protection during an accident. It relates to this thing, all right? In all cases, when you're crashing, we're going to have that same change in momentum. You had an initial momentum. Right, so you have some initial momentum, right? So my PI is equal to, we're just going to call it P. But in all cases, our final momentum is going to be 0. In a crash, you're coming to a stop, right? As a result, that change in momentum is going to be 0 minus P or negative P, right? So that's going to be the same for all crashes. So we're looking at the fact that that impulse is always going to be that negative P. All right. Let's go ahead and, for example's sake, give it a number. Let's say we have an impulse of 12 Newton seconds. Right? If you have a thin steel helmet, you're going to come to a stop very, very quickly. Right? That means your time interval is 1 second. When we look again at that force times time interval, we can see the fact that force is equal to impulse divided by time. So we put this in here. We see a force of 12 newtons. That's a lot. Now let's say we get something squishier, something that is going to make that time come to a stop much larger. Now we're going to say the fact that my time interval, same impulse, but now our time interval is 3 seconds. So now we can look at the force is equal to 12 Newton seconds divided by 3 seconds. Well, now our force is only 4 newtons. Right? So by increasing that time, we're decreasing that force. Right? So a thin steel helmet is going to offer little protection during an accident because the time it's bringing you to a stop is too small. You need something that has squish to it to extend that time to minimize the force of impact. All right. So that goes ahead and brings us to number 28. For number 28, we're doing some calculations. In a typical golf swing, the club is in contact with the ball with 0.0010 seconds. So we have a time interval of 0.0010 seconds. We have a 45-gram ball, and we have a final speed of 67 meters per second. We want to know the magnitude of force exerted on the ball. All right. I went ahead and jumped to the fact that this was our final speed because it acquires a speed. So it tells us this is the speed it's going to end up with. Generally speaking, in golf, the ball is not initially moving. So our initial velocity is going to be 0. Right. One thing we do need to go ahead and address is the fact that this mass is in the wrong units. Grams, while a wonderful unit in chemistry, is not very useful in physics. We use kilograms. So we are going to go ahead and multiply this by the conversion factor. All right. We want kilograms, so it's going to go in the top, and we're going to get rid of grams, so that goes in the bottom. There are 1,000 grams in 1 kilogram, so 1 kilogram over 1,000 grams. And that means we're going to divide 45 by 1,000. All right, and we do get a mass of 0.045 kilograms. All right, so we've got all of our variables sort of sorted out. We know what we want and that kind of thing. So let's go ahead and identify our equation. We're looking for a force. We have a time interval. We have some difference of velocities, and we have a mass. Hopefully you realize that this is impulse. All right, so force times our time interval is equal to our final momentum minus our initial momentum. If I go ahead and expand this out into the individual pieces, F times delta T is equal to mvf minus mvi. My initial velocity was 0, so this term goes away. And I'm looking for force, so I'm going to divide both sides by delta T. Right. We have everything that we are interested in for this particular problem, so we can plug and chug. So 0.045 kilograms times 67 meters per second. And we're going to divide that all by our super, super tiny time. Right. And we do get a force of 3,015 newtons. Right. To sig figs, this does change. We do only get 2 sig figs here, so I am going to put it in scientific notation to make that happen. That's going to be 3.0 times 10 to the 3rd newtons. Mastering physics has been on a kilonewtons kick for some particular reason recently, so this could also be 3.0 kilonewtons. Right? So that's just something to keep in mind. Right. That brings us finally to our last question. Our last question is number 29. It's about croquet, which my family and I played on Easter this year. So we are looking at the fact that we have a 0.5 kilogram croquet ball initially at rest on the grass. So we have a mass of 0.50 kilograms. We have an initial velocity of 0 meters per second. When the ball is struck with a croquet mallet, the average force exerted on the ball is 230 newtons. If the ball's speed after being struck, so final velocity, is 3.2 meters per second, how long was the mallet in contact with the ball? How long sometimes can talk about distance or x. In this particular case, you have to use context clues to realize that we're talking about time here. How long is time? So we're looking for that delta t. Hopefully you realize based on the variables we have, we're running into the same sort of problem as we had before. So we are looking at that force times our time interval is equal to mvf minus mvi. Our initial velocity was 0, And instead of solving for force, this time we're solving for time. So we're going to divide both sides by force. So delta T is equal to mVF divided by F. We have all of our pieces. Everything's in good units. We'll go ahead and plug and chug at this particular point in time. All right, we get a total time of 0.00695 65217. All right, that's obviously a little long. We do get 2 sig figs here. So delta T is equal to, we look here, the first non-zero digit is 6. We're going to keep the digit after that, but we need to look at the digit after that. 5 is larger, so it's going to cause us to round up. Well, 9 rounds up to 10, so that's going to round up. So we're going to have 0.0070 seconds. We can also go ahead and put this into scientific notation. 7.0 times 10 to the negative 3 seconds. Or if you are feeling like using our prefixes, it's going to be 7.0 milliseconds. So that is what we are looking at here. Hopefully you felt good about this and you are getting a good understanding of momentum. Please reach out with any questions.